Kia ora and welcome to video 17 in the series Insightful Integration. There are 25 videos in total in this series, so we're definitely over halfway now. This problem here is definitely a scholarship question because it involves parametric equations, it involves polar coordinates, and it also involves an area formula that you're not expecting in an NCA examination. This problem came from a friend of mine at St. Kentigern College. Shout out to them. If there's any of you St. Kent's students watching, feel free to comment down below. Dr. Snedden gave me this problem. He's a wealth of calculus knowledge, and he always has really interesting problems to work on. So this one is definitely no exception to that. The hardest part of this problem is working out your limits of integration, because you're given the area formula there, which is pretty nice, and you have to just substitute the R equation into it. You need a little bit of knowledge of trig identities to be able to integrate the expression, but the limits themselves, the lower limit and upper limit of t, is the insightful stuff that you need to be able to solve this problem. You're showing that the central regions of the two patterns have the same area. Anyways, good luck with that, and after the intro music, we'll go through the solution. To start this problem, I'd like to explain the area formula here. So this is when a curve is described in polar coordinates. First up, you might notice a similarity with the way that this is structured, because a circle in parametric coordinates has the equations r cos theta and r sine theta, and all that is it comes from trigonometry. If we have some point P x, y in the Cartesian plane, we can describe it using an equation with x's and y's, a Cartesian equation, or we can describe it in polar coordinates by saying how far from the origin is the point xy. We'll say that that's r, and then how far around from the x-axis. We go anti-clockwise, that's the convention. So we can describe points using left, right, up, down, Cartesian coordinates, or we can describe them in polar coordinates in terms of r and theta. The two equations there, r cos theta and r sine theta, just come from trigonometry. Of course, this side here is r sine theta, and this side here is r cos theta, so that's the connection between polar coordinates and Cartesian coordinates. Now, a circle is when the radius is constant, so r is 3 or 5 or something like that, but for this particular problem, the r value is not constant, so as we move around from the x-axis around anti-clockwise, the radius of the thing we're drawing is changing with respect to the sine curve. So we've got this r of t equals 4 plus sine of a times t, where a corresponds to the number of petals. So if we look at this problem here, a is 5.5 as the first one, a is 1.5 as the second. Let's look at the 1.5 one. So 4 plus sine of 1.5t. If we were to graph this, the sine part of the function here, the sine part of this radius, that alternates between -1 and 1. It has an amplitude of 1, so the radius is going to get as large as 5 and as small as 3. And then this dude in here, the frequency, 1.5 is equal to 2 pi divided by the period. Hopefully this is not unfamiliar to you, that you might have done the trig modelling internal. So if we look at that, the period of the graph, a period of a sine function is normally 2 pi, but this one is a bit different. The period is equal to 2 pi over 1.5, which is 3 over 2, which equals 4 pi over 3. So the sine function starts off at its middle point, 4. It increases to a maximum, it decreases to its minimum, and then it's back to 4 at an angle of 4 pi over 3. And 4 pi over 3 is 4 lots of 60 degrees, 240 degrees. So if we look at this shape up here, and I'm going to bring up Desmos in a sec, but this here corresponds to theta equals 0, and the radius there is 4. And then if we go around, we actually follow this outer thing first because the radius gets bigger and bigger and bigger. That maximum here, this maximum radius of 5 occurs at pi over 3, or 60 degrees. We can see that in this picture here. When it gets to 60 degrees, that is the furthest away from the origin. It's 5 away from the origin. When it gets to 90 degrees, it's actually closer to the origin, right? It's 4 point something. So if we follow that round, we get to a radius 3 away from the origin. We don't think of the x value as being a negative. It's the r value, the distance from the origin. So that's 3 there, and that's at theta equals pi. And theta equals pi is here. So we've got pi over 3 at its maximum, 2 pi over 3 there, 3 pi over 3 at its minimum, or pi. And then we keep going around, and we get back to where we started at 2 pi, and we haven't even done this inner region yet. The question asks us to find the area of the central region, and we haven't even got to that yet on the curve. So one of the things we need to work out with this integration, this integral formula that we're using, is what limits to use. And what we need to realize is that if we start at 2 pi and we go up to this point here, which turns out to be, gosh, what is it? 2 pi plus another 120 degrees. So this angle here is 2 pi over 3, but it's also 2 pi over 3 plus another 2 pi, a whole revolution. So if we add those two things together, we get 8 pi over 3. So that's our region if we wanted to find this area here. We're not integrating below a curve. When we use this area formula, half r squared theta, it's about time I explain what that actually does. It's area when we're in polar coordinates, half r squared d theta. Now it looks a bit weird because you're integrating a function in terms of r with respect to theta, but what that means is if you have some random curve, let's say some random curve which is described in terms of r and theta, so it's a function of theta, and if you want to find the area of this sort of sector, now it's not a perfect sector because the curve isn't necessarily a circle, but if we break it to a small angle d theta and we treat it like a sector, then this value here would be the same as this value here. Now technically it's not, right? I've just told you for the last 5 minutes that the radius is changing as theta changes, but if we're talking about a very small sliver of a piece of pi, then these two sides here are essentially the same length, and that's what we assume when we have some function and we're trying to find the area below a curve. So we'd say this is a function of x, and we treat this y value exactly the same as that y value, even though they're not, because we've got a small slither here. And we say if they're the same, it's essentially a rectangle, and the rectangle is an area of y times dx, and then we integrate to add up all of those rectangles. Well, same thing here, that if you want a sector, which is essentially a sector, a small slither of a piece of pi, and we want to find the area of it, well, the area of a sector, the formula for that, if you're in radians, is a half r squared theta. And then we're just saying, well, hey, the angle's not theta, it's d theta, and if we integrate it, we get this formula here. Okay, so when you see a formula like this, you're not expected to understand it, you just use it. They're using t in the problem instead of theta, but I've just described what t is in terms of angles, and the only thing that we really need to understand is the limits of integration. Okay, so we're ready to solve this problem now, but like I said, I'm going to show you a Desmos graph first. Prepared this earlier. This is for a is equal to 1.5, and the graph there shows you from 0 to 2 pi, it's the outer curve, and then from 2 pi to 4 pi, it's the inner curve. and we're starting at 2 pi and we're going up to this value here, which was, what value was it? 8 pi over 3, and that's going to give us the area of 1/3 of the inner region. Then we'll times it by 3. The A value of 5.5 looks like that. Okay, so if you notice, all the whole numbers correspond to the number of petals, but all the fractional values generates two different curves, because when you go from 0 to 2 pi, you're kind of like out of phase. Then the next time round you get a different curve, and then you're back in line with the starting point. Whereas with a whole value like that, when you go around from 0 to 2 pi, you're back to where you started. Okay, so for this one, I'm going to have to change my limits of t to fractions of 11, because the 5.5, I double that. And then go around the curve starting at 0, I get to 2 pi and I'm there. And then if I add in pi's of 11, that's 2 pi plus, it's a hard one to snap onto it, that's 2 pi, that's another pi of 11, and that's 2 pi plus 2 pi of 11. And on our diagram, it's going to give this region here, the area between the origin and the R value, which corresponds to theta equals 2 pi plus 2 pi of 11, and then we're going to have to multiply that by the number of arrowheads that we've got to find the area of the central region. If I stuff that one up, yes, I did stuff it up. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No surprises. Okay, let's get into the integration now. Alrighty, so for the first one, area is the integral between 2 pi and 2 pi plus 2 pi over 3, so 8 pi over 3 of this radius function squared, or we've also got a half. The radius function squared was 4 plus sine 3t over 2. And then the other one was a half starting at 2 pi and going up to 2 pi plus pi over 11. So 24 pi over 11, same function, so we don't have to integrate or find a different equation. It's going to be the same equation, just different limits. Alrighty, we need a trig to integrate this. The inner function here inside the squared is not a linear function, meaning we can't use reverse chain rule. So we need to expand out and then look at a trig identity. So if I just consider that r squared function, it's 16 plus 8 lots of sine 3t over 2 plus sine squared 3t over 2. And then that sine squared expression, because we want to anti-differentiate it, we need to use a trig identity for it. We're going to use the sine squared one that turns into the double angle cosine. So it's 1 minus cos 3t all divided by 2. It's a rearrangement of the double angle formula. Okay, so to integrate this, we've got area as a half integral from 2 pi to 8 pi over 3, 16 plus 8 sine 3t over 2 plus another half, so I'll add the half to the 16, get 33 over 2, and then it's a minus a half cos 3t dt. Okay, so we've got 33 over 2t plus sine goes back to minus cosine. Minus cosine 3t over 2 divided by 3 over 2 is the same as 2/3 in the front there. And then cos 3t, cosine goes back to sine when you're anti-diffing. So we've got minus 1/6 sine 3t. And then we've got a sub in 8 pi over 3 and 2 pi. Okay, so half 8 pi over 3 going into the first one. We've got 33 times 8, 264 pi over 6, which is 44 pi. The cosine bit, 8 pi over 3 goes into the and times this by 3 over 2, so you've got 8/3 times 3 over 2 is 4. Cosine of 4 pi is 1, so it's minus 2/3. And then the sine one, when you times 8 pi over 3 by 3, you get 8 pi. Sine of 8 pi is 0. So that's the first substitution. And then the next one, 33 over 2 times 2 is 33 pi. Cosine of the 2 pi goes in there, the 2's cancel. You've got cosine of 3 pi. Cosine of 3 pi is negative 1, so we've got plus 2/3. And then again, the sine bit 0. And okay, that if we work that out, that's 11 pi over 2. And then the minus 2/3, two of them, so minus 4/3 divided by 2 is minus 2/3. Now remember that the central region is actually 3 times that, therefore area central region is 3 lots of that, which is equal to 33 pi over 2 minus 2. I'm playing spot the error now because it doesn't quite match what I did earlier. Where is my mistake? Right, there is a 8 there. Well, I don't know if you spotted it. And so it needs to be minus 16 over 3. And then when we sub that in, it's going to be minus 16. That one there is going to be 16 thirds, and then minus, perfect. Okay, that's what I was expecting to get. Alrighty, now if we repeat that for the other one, and I'll leave you to check it, it's exactly the same antiderivative, we're just subbing in different limits. You will get to the same answer of 33 pi over 2 minus 16.